Coursera course, Constant Velocity Lab 1. Objectives 1. Discuss Newton's second law of motion. 2. Extract constant model from tracker. 3. Create a constant model from Python. 4. Make a spreadsheet combining our observational data from tracker and our computational model from Python. 5. Discuss questions asked in the assignment. Introducing Newton's second law of motion and momentum principle. The formula is stated in the next way. B final equal B initial plus F net. All that are all the forces that interact with our system. In this case, it will be zeros because we're talking about a constant velocity model. Divided by mass times delta t. If we apply a little bit of failure multiplying by mass, we get a new formula. Mass times B final equal mass times B initial plus F net times delta t. We call momentum to the product between mass and velocity, and that brings us to the momentum principle. P final equal P initial plus F net times delta t. As you can see here, this is our video I recorded. From that, I upload it to tracker and take the position in the positive x-axis and the positive y-axis. My calibration was 0.3302 meters and my origin in here. From that, we take our graph and you can see how it goes in upward in a diagonal straight line because it is a constant model. Also, we got our first interval time, second interval time, first position, second position, and our last time interval. From that, we can take our video analysis. That is, observation time starting is in 0 seconds. Car's initial position 0.003 meters. Car's initial velocity is 1.03 meters per second. In order to take an object's initial velocity, you need the average velocity formula. Delta in position divided by delta in time. In this case, our delta in position will be the second position minus the first position divided the second time interval minus the first time interval. In this case, our answer was 1.03 meters per second. Time lapse of observation was 1.833 seconds. From that information, we can make our computational model. Our car's mass 4.4 kilograms, well, our car position 0.003, our car velocity 1.03, our delta t 0.01, our last observational time 1.833. As I told you before, our F net in this case it will be 0 because it's a constant velocity model, and we apply also Newton's second law. We run it, and as tracker it should move in the positive x-axis, and that is what it did. Also, you can see how likely is the graph in tracker. So from that, we need to make a spreadsheet. We got our time from both tracker positions and Python position that is down. From that, we got the graph that is position time above Python and our observational data. As you can see here, both of them are very accurately, meaning that they match together in the same direction, and that's what we conclude, that it makes the similar movement. Now we got some questions to answer. When you analyze your video data in tracker, you made a choice of the orientation of the axis and how they will remain the same if you were to flip the axis. Well, in this case, in our observational model, I took the positive x-axis and the y positive axis. Well, in case that you change the axis, instead of having positive values in x, they will be negative. Also, the graph will change. Instead of going upward in a diagonal line, it will go downward in a diagonal line, because instead of going the positive x-axis, it will go in the negative x-axis. Also, what does it mean? Your observation can be predicted well by your computational model when you set the net force equal to 0 in your model. Is it possible for you to say how many pushes and pulls are added together to give 0 net force in the case that you observe? Of course, in this case, what will make this video of the car. In zero net force, it will be factors like gravity, frictions, and resistance. Thank you for your attention.